Good morning and welcome to video called How Do I Physically Determine Enthalpy? And this is something we'll be using in lab. So a couple things we'll cover here is what is enthalpy again. We had a video on that already, but we'll review what that is. How do I calculate it? And I'll just quickly refresh your memory how to calculate enthalpy. And this video mostly determines how would I get the enthalpy if I were to physically do this in lab? How would I physically do this? And then in order to learn this process, to do this in lab, we'll do some just-in-time learning. I mean, we'll learn a little something to help us figure this out. It's called how energy absorbed relates to temperature change. And I'm actually going to just change this color back to black. All right, so what is enthalpy? So if you have a reaction and you have your system, if your system is losing heat energy, okay, which would be heat meaning energy is transferring. In this case, it's in the form of, let's say, thermal. All right, then you are in the surroundings, all right? And you feel this heat giving off. We call that you're gaining it, it's losing it. Negative delta H, and this is going to be the amount of energy that is lost. All right, so enthalpy literally is the amount of heat energy that the system gains or loses. Negative means it's losing it. Positive means that this system is gaining energy. This to us would feel hot. To us, this would feel cold. Keep that. Don't ever lose track of that. Pretty simple. How do I calculate delta H? Well, we use our standard thermodynamic tables as a state function. The delta H is equal to the sum of the delta H of formation of my products minus the sum of the delta H of formation of the reactants. And that is pretty much all I'll mention on this right now. It's detailed in a different video. But how would I determine the amount of energy that a system gives off? And in reality, it's quite easy to understand. A little harder to do. Easier to understand that simply, if someone were to give away money, for example, if you have this guy were to just give away dollar bills, okay, and all over the place. Bill Gates, for example, losing money, you'd simply add up all the money that he gave away, and that's the answer. It's harder to realize how a system loses energy because, one, it's losing it in all different directions. So if I were to have a beaker, and this beaker is containing water, let's say we drop in here some solid NaOH, S there, drop it in, and then this stuff starts radiating energy to the water. The water's absorbing the energy, and therefore it starts to give off energy and eventually gives it off to the surroundings. If I were to blow this up into a bigger picture, okay, you would see the NaOH, as it dissolves, it breaks into Na plus ions, and then the OH negative ions, and then as this thing breaks, it radiates energy to the surroundings, and the water here picks up that energy. So the energy, the water is, in this case, our collector. It's collecting all of our energy. So whenever we have a system that's losing energy, whether it's simply a small molecule of NaOH, we have the system losing energy to the surrounding. We need some way to collect this energy. So, some engineers come up with the unique methods called a calorimeter. Now, a calorimeter is just a pretty simple device. There are all sorts of types, but essentially it's a glorified insulated cup. and we'll have some sort of insulator. Could be like this, just to keep as much energy as we can inside. And then inside here we have something that would be a collector. Now, water is a pretty common collector for us, okay? But we could have legitimately a piece of another type of calorimeter you might see might be something like this, where we have our insulator, all right, and then we might have, let's say, a block of aluminum, all right. This is all solid aluminum, and we have a little slot where we could drop something in, and this thing could radiate energy, and the aluminum would be my collector. Okay. So in this case, as far as collecting the energy, I need a collector, and that's really all it is. So the majority of this video isn't going to be really talking about necessarily the setup or the calculations of a collector or a calorimeter. It's more along the lines of, okay, what's the mathematics of the actual transfer of energy from an item lost to the item gained. We're assuming that the energy that the NaOH lost in here is equal to the energy that the H2O gained. All right, that is the premise of our calorimeter. Okay, if I know how much energy my collector picked up, then I know how much energy that my chemical reaction lost. Okay, now let's flip to a new slide here, and let's talk about one particular concept, and that concept is called specific heat. Okay, now this is a concept that I think is not as intuitive as some other ones. Okay, and the concept is basically the fact that as my system, okay, loses energy, let's just say it loses energy in all directions, radiating energy, okay, and just as in anything in nature, that as energy gets released, there are things that are collecting the energy. They're picking it up, absorbing it. And you would assume that, okay, and this really messed with people for a long time, you assume that if item A collects a certain, a specific amount of energy, and item B collects that same amount of energy, that the change in temperature of B would equal the change in temperature of A. And unfortunately, that just is not correct. Even if the transfer of heat is the same, same amount of energy is transferred, that there's not the same change in temperature. And that comes to the concept that we'll call specific heat. Okay? Specific heat is the amount of energy needed to raise 1 gram of a substance 1 degree Celsius. And this also is, by definition, what a calorie is equal to the amount of energy needed to raise 1 gram of water 1 degree Celsius. So technically, if we're dealing with things in terms of calories, then a calorie, the specific heat of water would be 1. All right, so 1 calorie per gram degree Celsius. That is the specific heat of water. Now, we don't generally use calories, we use joules, and since 4.18 joules equals 1 calorie, again, a lowercase c would be what I'm looking for here, then the specific heat of water is 4.18 joules per gram degree Celsius. That is the specific, that's the amount of energy you need to raise 1 gram of water 1 degree Celsius. Okay. So, unlike, let's say, for example, aluminum, so this is my H2O, and this is my aluminum collector. In that case, aluminum specific heat is 0.9 joules per gram degree Celsius. Right? 0.9, so less than, quite a bit less than this. So if two of these guys were to collect the same amount of energy, water would, again, they both get the same amount of energy. It's just that the reflection in the change in temperature is different. Okay? Their heat capacity, the amount of energy they're taking, is the same. Or we might even say this guy has a larger heat capacity. That's a different term. But heat capacity would be just the energy per joule per degree Celsius. So either way, if we make the masses the same, then it would be called heat capacity. Either way, so in this case, the way this works is, and I could show a simple example of this. All right, and I'm not going to go into large detail. We'll cover some of this in class, and you can pick up what you want. Let's say I have a block, okay, and we will do this in class. And let's say this block is 100 degrees Celsius, and let's say this block is aluminum. All right, and I drop this block into some water, and let's say the water is 25 degrees Celsius. Okay, so all right, you drop it in here, and I get this block. All right, it's in here, and the block is in here, and it's hot, so it starts radiating energy to its surroundings. Now, a few key points you want to understand is that energy will transfer from the block to the water until the temperatures are equal. Okay, it has nothing to do with the flow of energy, how much energy the water has versus how much energy the block has. Energy flows from areas of high temperatures to areas of low temperatures. LOW, all right, until they're equal, and then an equilibrium is established, and then we're good to go. So whenever I look at one of these problems, I create a little data table, okay, and we have, let's say in this case, the aluminum block, okay, and then we have my collector, which will be the water. H2O happens to be the item that's collecting my energy. We can solve a variety of problems off this, but I would list this out as being some various things that I would need. Would be my mass, okay, and the equation that governs this transfer of energy, the specific heat is, I'll put that up here, Q, which is the energy in joules, is equal to the mass in grams times the change in temperature, which is temperature final minus temperature initial, times C, the specific heat. Okay, and in class we'll detail a multitude of different problems. I'm just going to briefly discuss it here, but and you can seek other resources to get more information here. But the mass, I would need my specific heat, my temperature final, my temperature initial. This could also be listed as change in T, and then Q, my energy. Okay. I will say here that many of these things could be measured. In lab, the mass of the aluminum could be measured. The mass of the water can be measured. Specific heat is a data table item. We might even solve for this. Keep in mind, I have a multitude of variables here. Given every other variable, I solve for a missing variable. Okay. You have your temperature final, temperature initial, temperature final, temperature initial. At this point, my example does give me that the temperature initial of the block aluminum is 100 degrees Celsius. You also could make that 373 Kelvin. All right, and then my energy in Q, this guy here, I don't know what that is now, but I would say they are equal, but they do have opposite values. This would be a negative X This would be a positive X. This is the same amount of energy except the aluminum's losing the energy. So with that said, I'm not going to go into great detail. The mathematics of this particular system would be whatever energy is lost by the aluminum block is gained by the water. So I could draw up a mathematical or algebraic expression like this. The aluminum, okay, which would be equal to the mass. I'm mimicking this equation right here. The mass of the aluminum times the specific heat of the aluminum times temperature final minus temperature initial of the aluminum equals the energy that the aluminum lost. That is going to equal the energy that the water gains. So this is negative and this is positive. Will equal the mass of the H2O times the specific heat of the H2O, and then times the temperature final of the minus the temperature initial of the H2O. H2O. I will also point out to you, just so you know, that the temperature finals on these guys would also be identical. Okay? This is the premise of some mathematics where I would be given some of these variables and I'd solve for some other ones. This is about as complicated as I could make it, but there are other ways of substituting and doing some algebraic tricks just to make things easier. So, the calorimetry, what I would do is I would simply go back to my calorimeter and I would take my block, I would drop it in there, measure how much energy the water gained. Of course, if I know how much energy the water gains, mass times temperature final minus temperature initial times the heat. If I know how much energy this water gained, then I know how much energy the aluminum lost. A lot of times, we can just simply measure this as in energy, which is in joules per kilogram, potentially. Or if we're looking at a situation like with the NaOH, I can get myself a delta H for a reaction. I would say, okay, well, if I have NaOH going to Na plus OH negative, this is a dissolving reaction. It's actually quite exothermic. But in this case, I would take my reactions. Okay, well, I want to figure out this is in kilojoules per mole of this. So I could legitimately take 40 grams of this, which is equal to 1 mole, and I could dissolve that into some water. All right. Doesn't really matter how much H2O there is. I would include that in my calculation. And as it dissolves, it would give off a certain amount of energy. In that case, I would have my 1 mole of my NaOH, or the 40 grams, same thing. And I would figure out how much energy the water collected. That would be based on the calculations right here. Okay, based off this equation right here. I'd put my mass of my water in, change in temperature, specific heat, solve for the amount of energy that my water collected. All right, so then once I know how much energy the water collected, that equals the amount of energy that the water lost. That would be in joules. I would flip it to kilojoules. And then to get delta H is simply kilojoules per mole. Now in this case, I happen to use 40 grams, which is 1 mole. Energy per mole. And that is my delta H. Well, it's the energy for 1 mole. And since 1 mole of this went through the process, that would be my delta H. If the reaction happens to be a 2 in front of here, then I would have to account for that as well. But in this case, 1 mole of NaOH dissolving gives me that much energy. That's my delta H. If I used 10 grams of this thing, okay, that would be, rather than 1 mole, it'd be a quarter of it, so 0.25 moles. Then I would have less energy absorbed. I would end up getting a quarter of the energy that I would got before, and the fraction ends up being the same. So it'd be the 0.25 moles divided by the it would be the kilojoules of energy absorbed divided by the moles. I'd have quarter less energy and a quarter less mole. I would get the same delta H proportionally. And we'll stop there.